look at another calculation with cell potential. This one's a good one. We have a galvanic cell based on the reaction below. So we have some kind of a solution of aluminum. Maybe it was aluminum nitrate or sulfate or something like that. And we have solid magnesium. We're going to form solid aluminum and magnesium ions. They've already separated the two half reactions. Well, that was convenient. And they're both listed there as reduction reactions. What all do they want me to do? Eventually, I need to give the balanced cell reaction that's not balanced above and calculate the cell potential, E cell. Now, the whole balancing equation thing, people will get that confused. They'll be like, oh, looks good to me. There's like one aluminum, one magnesium, one magnesium. But the other trick with a redox reaction is that the charge needs to balance. And I do not think the charge is balanced. Okay, so let's do this first. Let's get that cell potential. And then, yes, we will need to balance this. To get the cell potential, we're going to look up those reduction potentials on a chart. It's at the back of your study guide. So we're going to look up aluminum plus 3 electrons forming solid aluminum. On my chart, the reduction potential is negative 1.66 volts. Fabulous. The second one, magnesium plus 2 and 2 electrons. Magnesium. Negative 2.37 volts. And again, I'm just looking these up on the chart at the back of your study guide. You would be given those numbers on the AP test. Okay, so again, these are in terms of reduction, but one of these has to be oxidation. Now, sometimes they might not give you that original equation, and they might just say, hey, here's the two half reactions. Write the balanced equation. And sometimes you'll say, well, I don't know. Like, am I really forming like aluminum and magnesium? I don't know. Well, no, one of these has to be oxidation. They're both written in terms of reduction, but there has to have an oxidation half. And how do you figure that out? You look at the cell potentials. You have to flip one of them for oxidation, and this thing will only run in a direction that leaves you with a positive cell potential. So you look at these two and you say, which one do I have to flip so that I can keep a positive cell potential when I add them up? Oh, that's not so bad, right? And then we'd say, we got to flip this guy. We're going to make it negative. I mean, well, we'll make it positive. We'll go opposite of that negative 2.37. We have to flip this one for oxidation. There has to have an oxidation half to match the reduction half. How do you know which one to flip? You have to keep a positive cell potential. If I flip that second one, I will be left with a positive. So let's do that first, eh? Okay, so now I'm going to have the negative 1.66 and positive 2.37 for an overall positive 0.71 volts. That's my E cell. And if you want, you can put the little degree in there. We're assuming that if we're not told otherwise, this is at standard conditions. 1 molar solutions, 25 degrees. All right, so there's part of it. We want the cell potential. And this does kind of match the overall balanced equation. I'm supposed to flip that second reaction. Magnesium is on the reactant side. The magnesium ion is on the product side. So you probably could have figured out which is oxidation reduction by looking at the original balanced equation. But sometimes they don't give you that. And then they'll say, hey, write the equation. And that's how you can figure out which one is oxidation. Which one do you have to flip? Okay, so now we're going to balance it. So we're going to have the aluminum plus 3 electrons forming aluminum, solid. Then we're going to flip the second one. So we'll have the magnesium solid forming the magnesium plus 2 ion. and 2 electrons. Yeah, the atoms and ions are balanced, but the charge is not. We have to have equal electron transfer. So in this case, with a 2 and a 3, we'll probably look for a 6, right? So we'll take this guy, and we're going to multiply him by 3. We'll take this half, and we'll multiply him by 2. So then if I go through, I would have like 2 aluminum, 6 electrons, and then here 2 aluminum again, and then 3 magnesium ion, and 6 electrons. Now my electron transfer is equal. Those should always cancel, and I can add these together to get the overall balanced equation. There'd be 2 aluminum plus 3 ions, 3 magnesium solid. I would form 2 moles of solid aluminum and 3 moles of magnesium plus 2 ions. Again, all the ions are assumed to be in solution. If you wanted to, you could go through and put aqueous by the ions. And then these neutral particles are the solids. There we go, balanced equation. Check. And again, we did not multiply those individual cell potentials by 2 and 3. That's the force pulling the electrons through the system. It's the same force whether it's pulling 2 electrons, 3 electrons, or 6 electrons. There's just more electrons going through the system, but they're being pulled through the system with the same amount of force. So we were okay doing that cell potential before we knew the fact that there were 6 electrons going through the system. It's one of those intensive properties. It's the same quantity regardless of how many electrons are going through the system. Okay, so we have the balanced equation. We calculated the cell potential. Now the fun part for all you artsy-fartsies out there, we're going to draw a diagram of the galvanic cell described above. Well, this is one of my favorite parts. Now, sometimes, again, they might ask you on the AP test to draw a picture of the cell, or sometimes they might have a picture, and they'll ask you to label parts. This is what I would be able to recognize. In a galvanic cell, you have 2 compartments, or 2 beakers. There we go. In those 2 beakers, there are solutions. And there are solids. Some kind of a solid electrode. Cool. Those electrodes are connected with a wire. There's probably some kind of a voltmeter up on top that's going to read our voltage. Cute. In the middle then, we should also draw the salt bridge. And then we'll label these. Oh, bummer, I'm going to run out of room. Let's move this thing over a little bit. You're probably doing the same thing. Oh, dang, I ran out of room. Okay, let's make that water. Whoa, it's blue. That's fine. Let's move my electrode over a little bit. There, then I think I'll have room for that salt bridge. Perfect. Salt bridge. There you go. Okay, so now let's start labeling everything. When you have a galvanic cell, it's usually listed an ox and a red cat. Electrons flow from the anode to the cathode. Oxidation involves losing the electrons. Reduction involves gaining. So they'll often put the containers in this order. They do not have to. So I would just kind of like double check that. I mean, probably 90% of the time they are in this order. So the anode should have my oxidation half reaction. Oxidation involved losing the electrons. That should be my magnesium half. So under standard conditions, this would be a 1 molar solution of some kind of magnesium ion. Maybe it's like magnesium nitrate or chloride or something like that. Then this would be the magnesium electrode, a solid piece of magnesium. What's going on at this half? Okay, so we've got magnesium ions in solution. And if I look at this half reaction, I'm supposed to form magnesium ions. So the concentration of this magnesium ion is going to increase over time because we're losing solid. The solid magnesium will form magnesium ions. So I should know that in solution, this concentration will increase and forming more of these positive magnesium ions. And we should make note that the mass of this magnesium electrode will decrease as I form magnesium ions. The other thing we should make note of, the salt bridge. If we're forming positive magnesium ions, this solution is going to become too positive. We want to keep this solution neutral, which there would be some other spectator in there. Like for every mole of magnesium plus 2 ions, there's probably like 2 moles of nitrate or whatever it would be. But I'm not changing the amount of nitrate or whatever my negative spectator is. I'm increasing the amount of the positive ion. So to maintain a neutral solution, this salt bridge would also be filled with some kind of spectators. Maybe like, again, nitrate. And then a negative spectator ion from the salt bridge would enter this solution to help keep it neutral. Okay, and the only other thing that I might put in would be the electrons. I form that magnesium ion plus 6 electrons. So there will be 6 electrons buzzing through the system over to the other half. Here comes my 6 electrons. Okay, half done. The reduction half. Let's scoot that down a little bit. The reduction half involved gaining the electrons, oil rig. That's my aluminum half. So this again would be some kind of a solution of aluminum. We'll make it 1 molar so it's standard. Some kind of aluminum solution. Again, maybe like nitrate, chloride. Those are probably the most common. Maybe sulfate. Something that's usually a spectator. All right, this would be my solid aluminum electrode. As we run the reduction half reaction, I'm going to consume those 6 electrons and form more aluminum solids. So this mass will increase. Where does the aluminum come from? The aluminum ion in solution. As the electrons are picked up by this metal becomes negative. Well, these positive aluminum ions are attracted to that metal then. As they pick up the 6 electrons, the aluminum ions will form solid aluminum. This concentration will decrease. So as the concentration of positive aluminum ions decreases, to maintain a neutral solution, some kind of positive spectator from my salt bridge will enter in. Often something like sodium or potassium. In you go. So maybe this was originally like a sodium nitrate solution. Very, very common. Where everything is spectators, the sodium and the nitrate won't react with anything in the solution. They're really just there to help maintain a neutral solution. Wow, isn't that impressive? And the only other thing, if you really wanted to brag, because you're so smart, you could put the voltage on your voltmeter. This should read positive, like 0.71 volts. That's what you should know about a galvanic cell. I know how to calculate the cell potential, and I know how to label or draw these parts. I'd be able to figure out the oxidation half at the anode I would know that the solution is becoming more positive as you increase the concentration of that positive ion. So the negative ion from the salt bridge will enter in, help keep it neutral. The mass of the electrode will decrease. The solid magnesium forms magnesium ion. We'll lose the 6 electrons. They're picked up on the other half by the solid aluminum, which then creates kind of a negative electrode. The aluminum ions in solutions are attracted to the negative electrode. We'll decrease the amount of aluminum ion as we form more aluminum solid. The positive ion from the salt bridge will enter in to maintain a neutral solution. These are kind of fun. If you get that, there it is. There's electrochemistry. Good stuff.